initial guess. And also use this. So this one is a vector, but this one is a matrix. The simplest choice is a diagonal matrix for H0. Then what happens is for K is 0, 1, 2, etc. Hopefully it will converge. That we compute, for example, the gradient. Okay. As the gradient valued at xk. Okay. Then we compute the descent direction, okay, such that it is minus h times gk. Okay. All right. And then we move in the descent direction such that we do a line search, we find alpha k equals, so arg minimum, I'll emphasize here is alpha is greater than or equal to 0, not strictly greater than 0, because it might not be achieved. So that what is the minimum value of this function if we move in the descent direction? Okay. And then we move in this descent direction. Okay. So these two can be combined in the same step if we can find a formula. Okay. And last.
Is alpha is greater than equal to 0? Minimum, the below minimum.
Yes, alpha greater than or equal to 0. So alpha may be 0 because D might not be a descent direction. So if we want to find the odd mean, it is actually 0, because if we search along the ascent direction with a step size that is positive, the function value will not decrease. So that's why it's kind of slightly different than the step distribution. So last step, the most important step, okay, that is update. HK plus 1. From H. Okay. All right. So our hope is so this is our hope. So our hope is in the sequence of H sub k approximates the Hessian inverse at kth iteration. So if it's exactly equal, this replicates Newton's method and has quadratic convergence, superlinear convergence that is super fast. So this is like the historical background of quasi-Newton method. That is, Newton method is too expensive, and we want to. But also, we demonstrated last time, Newton method was applied on general differentiable function, which in our case, which is this, okay, might not be a gradient descent method, so it may reach like a maximum. So that's also unfavorable. So the quasi-Newton method historically is proposed by like several engineers to address these problems. And so this is a workflow. So the workflow is very similar to what we have learned. For example, this one. This one is very similar to CG. We want to find the descent direction. So this one is line search. It's the same as the steepest descent. So what we learned in this one. So then we derived what we called, I don't know, what do we call it? But we derived an equation that HK, so we derived an equation what we want HK plus 1 to satisfy. Okay. We want HK plus 1 to satisfy this. Okay. So where this is, so the delta GK is a difference in gradient. So this is gradient of all right. And delta XK is a difference in X. So the intuition is in this way, okay? So this H approximates our Hessian inverse. So intuition in 1D, so we went through this last time. I mean, memorizing this equation is not very difficult. Okay, so we just memorize, we just have to acknowledge that f double prime at some point, okay, xk plus 1, so in 1D, yeah, let me still write it there. Intuition 1D is f double prime fk plus 1 can be approximated by the difference quotient, that is xk plus 1. This is 1D, okay, so in n dimension, we have to use matrix inverse, which is our form. Right, this is calculus 1. Okay. So everything we used roots from calculus 1, that we compute the derivative and we approximate the derivative using difference quotient when we take the limit. All right? So now think about this, okay? Now what happens is, if we write this equation, so if we rewrite this equation as what? As we move, we divide this to the right and we multiply this to the left. What we will have is f prime, okay, xk plus 1 inverse. Double prime is like our Hessian in n dimension. Multiply with f prime, xk plus 1, subtract f prime, xk, equals xk plus 1, subtract xk. Okay. So we hope to use, so we hope to use hk plus 1 to approximate this. So this is the whole idea, but in ND. Okay. But this equation is like in n dimension, so so hk plus 1 approximates, okay, the Hessian inverse at xk plus 1. So, and last time we learned a formula called SR1, okay, or SGS. So single, sorry, SRS. So single rank symmetric or SR1 or symmetric rank 1, okay? So S1 update to get HK plus 1. So what we derived was so this rule is defined as okay. So all we write it as a tensor product, that is so this vector z, so z, the transpose, or zk in Rn. This zz transpose is, we have a vector, then we take its transpose, we get a row vector, and when we multiply these vectors together, so we'll get an m by m matrix. So this is m by 1, this is 1 by n. We multiply together, we get a m by n matrix. That is rank 1. Okay. This matrix has rank 1. And most importantly, so keep this in mind, our Hessian, okay, so Hessian is symmetric. Okay. Our Hessian is symmetric, and so then this is a straightforward fact to verify. Any symmetric matrix inverse must be symmetric as well. All right. So not just this is rank 1. The nicest thing about this type of update, question?
Yeah, okay, so the Hessian is symmetric, but the Hessian is not HK. The Hessian is...
Yes, so I'm saying, so this is our motivation. So if a matrix is symmetric, its inverse must be symmetric. If we want to approximate a symmetric matrix, we want to use symmetric matrix to approximate symmetric matrix. So we create an update rule that maintain the symmetricity. So this update is symmetric as well. So this matrix, this Z times Z transpose is symmetric as well. Okay. So what happens is we create a rule that maintain our update symmetricity. Okay, so we use a sequence of symmetric matrices. Yes.
Sorry, we're just trying to figure out, so is HK the Hessian or not?
No.
Okay.
It's an approximation. So because HK, if HK is Hessian inverse, it replicates Newton. Newton is expensive. So this is a thread of thought.
Okay.
So Newton is expensive. Okay. We don't want to compute the Hessian inverse, so we use a sequence of cheap update to get HK. as approximation to Hessian inverse, because Hessian inverse will give us the direction that decreases fastest.
This sequence also must be symmetric because like
Yes,
the
yes,
last
we
year
will show some theorem, like because rank 1 update actually replicates CG, conjugate gradient. So because we want to, so the idea is the symmetricity of HK actually gives us this Q orthogonal, replicates this Q orthogonal direction, like this sequence of update of Q orthogonal directions in CG. So if we design this scheme, so like everything is connected. So I think if we read the paper like by Fletcher, which is one of the names in the state-of-the-art BFGS quasi-Newton method, that letter F. So in the original paper, what they did is actually they want to replicate CG by using, so CG has the unfavorable property of CG. It has two updates. Okay, like you have to do this orthogonalization, but somehow they simplified it, and they find, oh, this is like a new method because they actually achieve faster rate of convergence than CG. We can prove for quadratic function, quasi-Newton actually achieves super linear convergence. It's like in between CG and Newton. Okay, so all right. So this means what? This means if HK is symmetric, okay, we add a symmetric update to it, then HK plus 1 is symmetric as well. Then okay, so this is also when we do our research, so let me be honest, when we do our research, I mean most of the nice stuff has already been studied, let's say this, okay, by those great mathematicians in the 20th century. So if we want to do research related to optimization. So then what our new method tries to do, for example, back in the 60s, what Fletcher tries to do is they try to design CG first, okay? They try to replicate CG first. So when we propose a new method, we have to replicate the older result first. Okay, so that's like a lesson from this. But now let's again derive this. Okay, so now let's plug in the update to this equation. So HK plus 1. So this is the equation we hope our HK plus 1 satisfies. And we plug in this update rule, we will get this is HK. So we plug in this. So let's name this S. So we have this is, so HK delta GK plus this ZK transpose. Times gradient of GK difference between two consecutive gradient, and this is this guy, so we keep it as it was, okay? So we basically we replace this guy with our rank 1 update formula. So the key is we don't compute this as a matrix times a vector. Instead, we compute this inner product first, and then we compute this. So overall, if we do this computation, okay, so its computational complexity is order n. And if we have order n complexity, n is our number of variables, degrees of freedom, number of parameters in a neural network, then this is a nice algorithm. So then we have, so now we have zkth iteration, and this becomes the inner product of these two. Okay. Equals. So this is a scalar now. It's like a coefficient. Okay. So now we solve for zk. So we get zk is. So we subtract this term to the right. And then we divide this number. Right. So the bad news is zk appears on the left and the right side of this equation. Okay. So we still need to figure out what is this. So luckily we have a trick to get this using our homework 1. What happens is we multiply equation number 1, left and right, with this delta gk. Okay. So inner product with then what we have is, so this is hk delta gk plus, so again, this guy is a scalar. Okay, so this guy is a scalar, this guy is this. So we can pull it in front of the inner product. That is zk delta gk. Okay. But then we have another zk inner product with delta gk, so actually we get this guy square and equals which equals this guy inner product with gk. Alright. So now we've derived this square, which is zk delta gk square is equal to, so we subtract this term to the right. We have this is delta xk, subtract hk, delta gk, delta gk. Okay. Now we look at the formula. Now we're ready to derive our full rank 1 update formula. Alright, so what we have is hk plus 1 equals hk plus zk times z transpose. So this is our zk. Okay. So this is our zk. And zk times z transpose, this top of the numerator is a vector. So it's this times this same thing transpose. This is a scalar. This is a number. So we square it. So what happens is we get this, the top, which is delta x subtract HK times delta GK times this vector transpose, okay, so that we get a matrix. And then in the denominator, it is ZK delta GK squared. But then ZK delta GK squared, we've expressed it in this way. ZK is the thing we want to find. All right, we can't leave ZK here. So now we simplify the notation a little bit. So we let EK is in this guy. Okay. So think about this. We want this to be as small as possible. Yeah, because we want so we hope. So this is our hope. Our hope is HK approximates the Hessian inverse at each iteration, right? So, and the Hessian inverse, all right, satisfy this equation to some degree, like up to the second order accuracy, okay, by Taylor expansion. So this is like a small quantity, right? So this is the first thing we notice. And then we replace, once we replace this with this, and every notation, so we'll get a very compact formula. That is, HK plus 1 is HK plus, all right, on top, it is EK tensor product with EK. In the denominator, this is our EK, all right, EK inner product with delta GK. So this is our SR1, or so this is our rank single, rank symmetric. So this is SRS, or the famous symmetric rank 1 update of the Hessian inverse approximation. All right. And this one satisfies. So because so this is our starting point. So in this way, in this update, HK plus 1 satisfies this equation. If we in SR1. So okay. So it approximates Hessian to some degree, like up to the second order accuracy. If again, if we like expand f up to like a quadratic term, so if HK plus 1 satisfies this equation, it approximates Hessian at the next iteration. So at the current iteration, by order a square, like this accuracy, because Taylor expansion, if we expand to quadratic term, so we have this approximation. It's like the linear approximation of the Hessian. So, and then the next important property we want to verify is, so what we have is this. So this is what we have, okay. In fact, what we want is actually this. So if it has something like this, all right, this is even nicer. So now if we have this, it really replicates conjugate gradient. And this is what we want. All right. So later we will show, like actually today we will show that when we have a quadratic function, this is indeed satisfied. And later we will show how we use this relation to replicate CG for quadratic function. So a lemma. So if f of x is our old friend quadratic function with q symmetric, positive, definite, okay. Then the SR1 update satisfies, okay, the thing we want. So this thing will be needed to prove that the quasi-Newton actually replicates CG for the quadratic case. All right, now let's look at how we show it. So when I equals k, this is automatically true because actually we went through this whole derivation to let this update satisfy this equation. Okay. All right. So now it suffices to show that suffices to show this is true for I is less than k. Okay. So, and we want to show this using our own friend inner product. Okay. So instead, this is a very common way of showing things in optimization or in general any analysis performed under the Hilbert space framework. Okay, that is, we consider a vector. We don't consider itself, but we consider its representation using the inner product with other vectors. You know, so. This is also the idea of this reproducing kernel Hilbert space, also the backbone of the famous transformer neural network. That is, will represent, for example, a word token, not by this vector itself, but by how this vector interact with other representations from other words, which gives us our famous GPT. But yeah, that's another story. So we'll go through this. Not go through this, but we'll talk about it next semester. So now let's look at. So if we plug in the formula of the rank 1 update, okay. So the left side of this is in this, right? So now we plug in the rank 1 update formula. So we will get okay. So which is this guy inner product. So this guy times this, which is plus 1 over EK delta GK. Then this is EK, okay, tensor product with EK matrix multiply with delta GI. Okay. So again, so if we have, so we can use this identity. I mean, A tensor product with B matrix. So let's not use C, let's use B, okay? This is the same thing as, okay, so A times B inner product with B. So now we do the same thing. We find this is we replace this formula by, so this is a scalar now, so we put this in front, and we have this is EK inner product with delta GI. Okay. This EK. Now we expand. Okay. So think about this. All right, think about this. So we can prove by induction. So if we want to prove by induction is next. So after we observe this formula, we want to prove by induction. So how we do it is we assume the theorem holds for HK. All right. So i.e. it's HK delta GI is equal to delta XI when I is 0, 1 up till K minus 1. Up till K. Okay. Let me see. Yes, up till K minus 1. Okay. Or, in other words, to say this is I is less than. Okay. So by induction hypothesis, if we want to do this, so this is called induction hypothesis. So by induction hypothesis, alright, so this guy is already what we want to prove. So this is delta xi. Delta by induction hypothesis, this term is already delta xi, which is the next thing we would like to prove, and which means this thing, when we're doing this inner product, it must be 0. Okay. So how do we show it's 0? And let's expand this EK. So we rewrite this as this. This becomes delta x k subtract h hk delta gk inner product with delta gi. Okay. Now we want to use a trick. And this trick is a very nice trick. So we consider this term first. Okay. So we consider this term first. So what we consider is hk delta gk inner product against delta gi. Now we have to use the symmetricity of the HK. Okay. So because SR1 update is symmetric. Okay, what does symmetric mean is, right? So if A is symmetric, put it here. Then X transpose AY, this guy, is a number, okay, is equal to the transpose of it, which is Y transpose A transpose X. A is A transpose, so this is equal. All right. In other words, using our notation, this is like AX inner product with Y is equal to AY inner product with X. Okay, so this is a nice thing about this symmetric matrix. Now what happens is we move this guy like here. Okay. So what happens is this is equal to HK delta GI delta GK. Now, by induction hypotheses, so it's trick after trick. By induction hypotheses, okay, we already have this is delta x. Okay. And now we use another nicest thing about this is, that is, so because now we use f is quadratic, so because f of x equals 1/2 x transpose qx subtract b transpose x. Okay. So f's Taylor expansion is itself, and what happens is, so gradient of f Hessian of f at xk equals q for any k. The Hessian doesn't change. If the Hessian doesn't change, what happens is this guy, okay, the delta gk equals q times delta xk. Okay. So now we're back here, and what we have here is we replace this guy with q delta xk. Okay. Now we use symmetry again, so this becomes q. So q is symmetric. So delta xi. So I will play a few magic trick. And we get this, and then this is what? This is delta g I inner product against delta xk. So now let's take a look back here. So this implies delta ek inner product against delta gi is, so is this guy inner product with this, which is delta xk inner product with delta gi subtract hk delta gk inner product with delta gi, and we use a few symmetry property, and f being exactly quadratic, we have this term is this. And by the commutativity of inner product, A inner product with B is the same as B inner product with A, so we got 0, so which means this term is indeed 0. And by induction, and we proved our theorem. So this theorem will be our basis to replicate, to use quasi-Newton to replicate CG. Okay. So let me see if I want to go to rank 2 update. Okay, but let's not go to rank 2 update, but let's just go back to the rank 1 update formula. So to motivate us, so next class we'll talk about rank 2, and then we'll learn how to implement next Thursday. So let's look at rank 1 update formula. So this is our rank 1 update formula. Let's look at the following thing. Okay, so if we have some vector, which is A tensor product with A itself, for A is an Rn, then this matrix, okay, is greater than or equal to 0. What does it mean is if we multiply it with a vector, so for y in Rn, okay, for y in Rn, y transpose is A transpose y, which is, we combine the first two, which is A transpose y, okay, transpose. So this guy, okay? This guy is a number, so its transpose is itself, which means this is, so this is greater than or equal to 0. Okay. Of course, it can be 0 if A is orthogonal to y, okay, which in n dimension, it happens all the time. Think about this. So in 3 dimension, okay, if we have a vector A, and then it's orthogonal to a plane, so we have infinitely choice of vector to make it 0. So this is only greater than or equal to 0. However, if we ignore the numerator, we add a greater than or equal to 0 matrix to a positive matrix, okay, we will always get a positive definite symmetric matrix, okay, if we ignore this term. So now we cannot ignore this term. So what happens is, so we know this one is known to be positive, non-negative, sorry. So when we add this term to, so this, we hope, okay, by construction, so this is we hope, by construction, we hope this guy is positive because it approximates a positive Hessian. So we hope by construction that is positive. That's our hope. So unfortunately for rank 1 update, this is not true. It's because, however, so this number, this is a number. This is this guy in product with this. And keep in mind, okay? We said in the very beginning of the class, so what's EK? So let's remind us what's EK. So EK is defined as delta xk subtract hk times delta gk. Okay. So EK is a small quantity because we hope this equation is satisfied when HK replaced by HK plus 1. So, and every time we just modify a little bit HK. So this is a very small quantity, okay? This is a very small quantity, inner product with something. So the magnitude of this is very small, which makes this small, okay? And this thing is in the denominator. So this is very dangerous, okay? So this magnitude is small, and this quantity might be negative, and then we divide a very close to zero negative term, then it drags this whole thing to nil. Like this matrix not positive anymore. Okay. And this is small, and the magnitude of this is small. All right. So combining these two, so this is a positive matrix, but it may have a negative factor. So HK may not be positive even if the HK is. Okay. So which motivated us to our next method, which is rank 2 update. So we won't go through this. So rank 2 update is way too long. So we kind of repeat this whole derivation, but now we use quadratic expansion for HK, so which is called the DFP method. But let's do this next time. Okay, DFP method. So the idea is we construct something like this. Okay. So this is like alpha EK. So this is another factor, but we add another beta, and this is delta xk. Tensor product is delta xk. So this is like a L2 regularizer term that makes this whole thing positive, and our goal is to figure out what is alpha, what is beta. So that's it for today. So next time we'll do this DFP method, and then we'll learn how to implement quasi-Newton.
So the goal is always to just make the HK1 positive.
And also satisfy this. Because if it's not positive, then using our template for quasi-Newton, when we don't have a descent direction, we may get an ascent direction that the function increases. And if we try to find the arg minimum, we wasted an iteration because we'll find alpha is 0. Because no alpha positive will make this function value decrease. So, and then we said, oh, the argument is 0, so the xk theory doesn't move because the step size is 0, so we stay there for another iteration. And then we evaluate this again. Okay, so it's ascent direction again, we stay there forever. You know?
So because like the SR1 has like a risk that could be like like negative, so we just go.
Yes,
like
so it may make next iteration's approximation to Hessian inverse negative, which we don't like, okay? Yeah.